And number 24, we want to solve this. And in order to solve this particular example, we could use logarithms and take the logarithm of each side, and that would allow us to bring the exponents down. But always look to see if you can write them as a common base first. The 27 I can rewrite as 3 to the third power. When I do that, I multiply the exponents. The 1/9 I can rewrite as 3 to the negative second power. I multiply the exponents. Again, with a fraction, just look at the denominator. 9 is 3 to the second, so 1/9 is 3 to the negative second. And now if I have a common base on each side, I can just set the exponents equal to one another, which means the 3x minus 1 and the negative 2 times the 2x minus 2 are equal to one another. And now I just distribute. That's a 3x minus 3. Here, this is a negative 4x plus 4. And now I just have to solve this. I'm going to add the 4x to each side. So that's going to leave me with a 7x minus 3 equals 4. I add the 3 to each side. So I get 7x equals a 7. Divide each side by a 7. And I find out that x equals a 1. Okay? And I can easily plug that back in and check it. Number 25, it asks us to use the properties of logarithms to rewrite this as one logarithm. Remember, two logarithms with the same base, which is what I have here being added, I can rewrite as, before I do that, let's see, I've got a 3 out front. Remember, whenever I'm multiplying something by a logarithm, I can bring that something up as an exponent. So I can bring this up as an exponent. So I'm going to rewrite that as log base 7 of 2 plus log base 7 of x to the third. And now two logarithms of the same base that are being added, I can rewrite as one logarithm of the two things being multiplied. So that's going to be log base 7 of 2x cubed. And now two logarithms being subtracted that have the same base, which is what I have here, I can rewrite as one logarithm of the two things being divided. So it becomes log base 7 of 2x to the third divided by r, all inside one logarithm. And that's it. That's my properties of logarithms. Number 26, I'm working backwards. I'm doing the exact same thing, but in reverse. So here I notice that I have two logarithms being divided. And since there's no base written with this logarithm, I know it's log base 10. It's my common log. But I'm going to rewrite this as log of 4y squared minus the log of 7. And now here I have two things being multiplied inside this logarithm. So I can rewrite it as two logarithms being added. So I'm going to do log base 4 plus, log of 4 and log of y squared minus the log of 7. And now right here, the exponent I can rewrite as multiplication. So when I do that in this final step, that's going to give me log of 4 plus 2 log of y minus the log of 7. And that's it. Now it's written as a sum, difference, and or multiple of logarithms. Okay? In number 27, it says to use the change of base formula for log base 5 of 18, and we're going to round it to 3 decimal places. Remember, our change of base formula, no matter which logarithm base we have, we can always change it to a logarithm base that we want. So I'm going to change this to the natural log, and you just do the natural log of what was inside the original logarithm over the natural log of the original base. And when you do this, make sure you put parentheses around each of those numbers. If you don't have that, it's not going to plug into your calculator right. And then when I plug this in, it gives me a 1.796. And that's it. Okay, so change the base formula. And again, you could use natural log or common log. Those are the two good options because they're on our calculator. In number 28, the first thing we want to do is we want to rewrite these as one logarithm. So since I have two logarithms with the same base being added, I can change that to one logarithm of the two things being multiplied. So it becomes log base 2 of, if I multiply the x minus 1 and the x, it leaves me with an x squared minus x using my distributive property. And now that whole thing is equal to the log base 2 of 6. And now to undo log base 2, I do 2 raised to the power of each side. So each side of my equation becomes the exponent. The log base 2 and the 2 cancel. So over here, I'm left with an x squared minus x. Over here, I'm left with a 6. And now I've got a quadratic equation to solve. I subtract the 6 from each side. So I've got x squared minus x minus 6 equals 0. And now solving a quadratic, there's a couple methods I can use for that. The first of which is always factoring. So I'm going to check factoring. I build a bridge, that's a -6. The two numbers are a -3 and a +2. So this factors into an x minus 3 and an x plus 2. I set each factor equal to 0. And I solve each. So here I add the 3 to each side. That gives me an x equals 3. Here I subtract the 2 from each side. So I find out that x equals a -2. And it would appear that these are my two solutions. However, with a logarithm, I can't take the logarithm of a negative. And I look, when I plug a -2 in here, that would give me a -3 in my logarithm. And that's no good. Here, if I plug the -2 in, I'd be taking the logarithm of a negative as well. And that's no good. So that means this is an extraneous solution. I can't plug that in. So my only answer is the x equals 3. Okay? Number 29, it says an investment of $1,000 is earning 6% APR compounded monthly. Find the number of years needed for the investment to reach $6,000. We're going to round to the nearest hundredth. So here I've got an investment. We're increasing, so this is going to be y equals a times 1 plus r raised to the t. And again, it's all about making our units match here. The initial investment is a, that's the 1,000. I want to know when this thing is going to equal 6,000. The rate is the 0.06. However, that's an APR, that's a yearly percentage that's being compounded monthly. So I need that as a monthly percentage. So 0.06, I have to divide by 12, okay, when I punch this in. And now I'm going to raise it to the t. And keep in mind, t is the time here, but the time is going to come out in months because my interest rate is now in months. All right. So as I start to simplify this thing, the first thing I do is I've got to divide each side by this 1,000. I've got to isolate the exponential part of the function. So that's going to leave me with a 6 equals. In here, I can simplify this a little bit. I can divide the 0.06 divided by the 12, and I can add that to the 1. And when I do that, that's going to be a 1.005 raised to the t. And now let me clear a little bit of space out here. Because now what I'm going to do to undo an exponential function, I have to take a logarithm of each side. And the easiest thing to do here is to take the natural log of each side. So I take the natural log of each side. And now using my properties of logarithms, I can bring this t out front as multiplication. Okay. So what I end up with is the natural log of 6 equals t times the natural log of 1.005. And now this has become a multiplication problem. To undo multiplication, I have to divide. So I divide each side by that natural logarithm. And now this becomes a job for my calculator. And really, it looks very similar to my change of base formula because that's another way we can approach this. And again, just make sure when you plug it into your calculator, you put parentheses around that 6 and parentheses around the 1.005. When I punch this in, it gives me 359.247 something. And I know I'm supposed to be rounding this off. However, this is in months, and I don't want this in months. I want it in years because that's what the question asked me for. Okay, so I have to divide this answer by 12 to get the number of years. And that's what I'm waiting for. I'm going to plug that all in, and I'm going to round it to 2 decimal places now, 29.94 years. Okay? So again, make sure you're aware of which units you're using and make sure they match. Number 30, we're using this equation, P of t equals 400e to the 0.12t. And it's important to understand what this means. The initial population here is the a value. It's this guy right here. It's the 400. And if you forget that, just put a 0 in for time, and you should get a 400 out for the initial population. The growth rate constant this time, the k value is up here. It's the 0.12. So make sure you're able to read these things and understand this exponential growth model. This is for continuous growth. And now we get to the nitty-gritty here. It says, what's the population after 1 week? And keep in mind, in our problem here, time is in days. So I am just going to plug this right in, but I've got to plug it in days. So I've got to plug a 7 in for time. Okay, so that's 400 e to the 0.12 times 7. All right, and again, when we plug this into our calculator, make sure that you're multiplying the 0.12 times the 7 before you do e raised to that power. Okay, so we're going to do e raised to that. It ends up being a 0.84, and then multiply by the 400. This is just plug it into your calculator here. 26.55. Okay. And that's it. And really over here, this is just notation. That doesn't do anything. It's saying P of 7, the population at 7 days.